Welcome students to the discussion on nuclear reactions, how they play important role in understanding the abundance evolution of elements. And in the previous lecture, let me take a quick recap of the previous lecture. I have discussed for photon induced reactions, how mathematically one can write down expressions for cross sections connecting the forward reaction cross section to the reverse reaction cross sections. The underlying main concept of this inverse reaction is following. I am repeating this every time so that you can get the actual point. At low temperatures, nuclear reactions with positive Q values, they play important role in the energy production of stars and also in the synthesis of elements. Now, at the low temperatures, because energy is not sufficient to the nuclei involved in the reaction to participate in a reaction with a negative Q value, at high temperatures where the energy of the nuclei will be equal to or more than Q value of the nuclear reaction, we can expect negative Q value nuclear reaction also proceed significantly. That is one reason. Number 2, practically many a times it is not possible to measure the cross section of a nuclear reaction of our interest. Reason could be anything. Maybe we wanted to come out with the energy liberated because of that particular reaction. What is its contribution to the overall energy production from the stars, or synthesis of new element? It could be any reason. But due to some technical difficulties, it may not be possible that that reaction can be carried out. In this kind of scenarios, researchers looks for the possibility to carry out inverse reaction. And one of the beautiful examples I have discussed in terms of gamma ray induced reactions. When a nuclear reaction happens, if one of the reaction products is gamma ray, then that reaction is called as radiative capture reaction. If that is induced by proton, then we call it as proton capture reaction. If it is induced by neutron, we call it as a neutron induced reactions. If it is induced by alpha, we call it as alpha radiative capture reaction. What about reverse process? If a gamma induces the reaction, then we call it as photo disintegration process. What is photo disintegration process? A nucleus absorbs the gamma of certain energy, then it decays into different products. Gamma plus type 3 nucleus gives rise to 1 and 2 types of nuclei. This is photo disintegration reaction. And in the last class, I have discussed how the cross sections of forward and inverse reactions can be connected to each other, taking the help of principle of time reversal invariance. And one more thing you have to remember is that till now there is no experimental data which says that this time reversal invariance is violated. So, at least for electromagnetic interaction and a strong interaction, it has been established that by taking the ratio of the forward and reaction cross section data, one can play the game. And after writing the reaction cross sections, I have written the ratio of reaction rates, and from the ratio of reaction rates we have seen the importance of one exponential term, and also I have discussed the dependence of this reaction rate, dependence of the ratio of the reaction rates on the Q value and also the temperature. I have given few numbers which has clearly said that the ratio of inverse and forward reaction rates is very much sensitive to Q value of the reaction, and it is more important at high temperatures. That means, at high temperatures inverse reactions will proceed significantly. So, this I have extended to photon induced reactions, and after that I have discussed energy production in stars. And while discussing energy production in stars, what I have done? I have highlighted the importance of non-deposition of energy by neutrinos, because the neutrinos are extremely weakly interacting. They pass through the stars, they come outside of the stars and reach the earth and different places in the universe as if nothing is stopping them. So, that is why it is quite challenging to detect the neutrinos. So, if you want to measure the energy produced by a star, and if you have the information of all the reactions, which I will discuss in detail in today's lecture, then one should ignore the contribution of neutrinos. You can always say, what about positron? Positron will immediately find electron in the surroundings and it will undergo pair annihilation, which gives 511 keV gamma rays, and those gamma rays, like gamma rays produced in other reactions, they will be absorbed within the star. And after that I have discussed the importance of lifetime of the nucleus, mean lifetime of the nucleus when it undergoes reaction with another nucleus. Okay. So, what was the expression I have discussed in the last lecture? The lifetime of nucleus, mean lifetime of the nucleus 1 when it reacts with type 2 nucleus is equal to 1 by number density of nucleus of type 2 and the reaction rate. Okay. So, what this equation tells us? The mean lifetime of nucleus designated by number 1 does not depend on the number density of the same type, because the lifetime of a particular nucleus depends on the number density of the second type nucleus with which it is interacting and it is losing its existence, it is ending its life. That is why the number density of type 2 decides the lifetime of the nucleus type of type 1, and the reaction rate per pair also decides the lifetime of the nucleus of type 1. This is what I have discussed in the previous lecture. So, based on this knowledge, in today's lecture, please let me focus on one of the fascinating aspects of the nuclear astrophysics. Coming back to the main objectives of the course, to understand the energy produced from the stars and also to understand the nucleosynthesis, the process of formation of new nuclei. These two are the main objectives of the course, right? Now, let me focus on one particular nucleus, say X. How mathematically one can represent the abundance evolution of time dependent abundance evolution of this particular nucleus. So, in today's lecture we are going to get the answer for this question, how to represent time dependent abundance evolution of a particular nucleus within a star. Number 2, a nucleus can be destroyed in more than a way. So, if nucleus can be destroyed by interacting with nucleus of type 2 or 3, the question is which one is more dominant in the destruction process. Okay? For example, if you consider a nucleus of type 1, it can interact with type 2, it can interact with type 3, right. For example, if it interacts with say some proton, it can undergo destruction. If it can interact with say alpha particle, it can undergo destruction. Which one is more dominant? Sometimes you can come across a nucleus which is radioactive in nature, So, it can undergo decay. So, it has lost its existence, but before it undergoes decay, if it reacts with another particle, then also it undergoes destruction. Which process is dominant? On what parameters the dominant process of destruction can be understood? Why it is important? because the abundance evolution of any nucleus, to understand it, you need to understand in how many ways the nucleus is produced and in how many ways nucleus is destroyed. That combination of processes decides the evolution of a particular nucleus. Okay? But before answering these two questions, number one, how mathematically one can represent the abundance evolution of a nucleus. Number two, how to understand the dominant process of destruction. Before answering these two questions, let me introduce a few parameters, okay, and a few important equations with the help of which we can answer these two questions. Okay. So, for that, let me continue the discussion with which I ended the previous lecture, that is mean lifetime of the nucleus. Okay. So, let us continue the discussion. For this, I am considering the same type of the nuclear reaction, that means 1 plus 2 gives rise to 3 plus 4, like a general reaction type I am discussing. Okay. Now, the rate with which nucleus of type 1 undergoes destruction, okay, by interacting with a nucleus of type 2, dN1 by dt, because of the presence of 2 is equal to minus lambda 2. That means, the decay constant of nucleus of type 1 and original density of type 1 nucleus, original number density of type 1 nucleus. This I can express in terms of lambda, okay, that is decay constant in terms of mean lifetime, can be represented as lifetime of mean lifetime of nucleus 1 when it is interacting with type 2 nucleus, type 2 nucleus. I hope this expression is clear to you. The rate of nuclei of type 1 with which it is undergoing destruction by reacting with type 2 nucleus is nothing but the number density of original number density of the type 1 nucleus, okay, and the lifetime of the nucleus 1, where lambda is 1 by tau, which is a decay constant. Okay. Now, I can also write this as dN1 by dt by interacting with type 2, considering the nature of identicalness, okay, delta 1 2, total reaction rate R12 is equal to minus 1 plus delta 1 2, okay, N1. I am writing the expression for total reaction rate R12, all right, sigma V, that is reaction rate per pair, which is involving first and second type nuclei, 1 plus delta 1 2. So, this and this will get cancelled. I can write down like minus N1 N2 sigma V 1 2. So, this Kronecker symbol appears, as I said, because for identical nuclei each reaction destroys 2 particles, okay, and from this I can write down a few more expressions like total reaction rate is equal to delta, okay, so I mean lambda, decay constant of type 1 nucleus when it interacts with type 2 nucleus, N1 divided by 1 plus delta 1 2 is equal to 1 by 1 plus delta 1 2 and N1 divided by tau 2 of 1. This is one expression for total reaction rate. Using this total reaction rate expression, I can write down the mean lifetime of nucleus 1 when it interacts with 2 in some useful terms, like following, okay, is equal to N1 divided by 1 plus delta 1 2, total reaction rate when first and second type nuclei are involved is equal to 1 by N 2 sigma V 1 2, okay, because I am writing here by substituting R 1 2 this expression, this equation in this place, okay, and here in terms of mass fraction I can write down like this: mass fraction of type 2 nucleus and mass of type 2 nucleus in AMU and Avogadro number sigma V12, all right. So, this equation helps us to find out the mean lifetime of a nucleus type 1 when it interacts with type 2 nucleus, and this is helpful in terms of some quantities like stellar density rho, mass of second type nuclei in AMU and mass fraction of the type 2 nucleus, and Avogadro number is well known. Of course, we need the value of reaction rate. Okay. So, this is one interesting relation which helps us to answer the question which is the dominant process of destruction when a nucleus can undergo in more than one ways of destruction. Okay. This formula I will discuss again in detail by taking one interesting example. Okay. So, then let me continue the discussion by writing expression for the decay constant. Okay. Decay constant, in terms of decay constant of type 1 nucleus when it undergoes in reaction with type 2 nucleus is nothing but mean lifetime inverse, right, is equal to same relation N2 sigma V12 and rho mass fraction of second type nucleus and mass of second type nucleus Na sigma V of 1 and 2. And the decay constant of the nucleus for destruction via any particle induced reactions like proton, alpha or any of the other particle induced reaction depends on the stellar density, okay, and on which further depends on the temperature basically, okay, through the reaction rate. And if type 1 nuclei can be destroyed by several different reaction, the total lifetime of first type nucleus can be represented as 1 by tau I of 1. Okay. Now, this expression is very useful and frequently they will be applied in several stages of nuclear burning processes. Do you remember in one of the previous lectures I have said there are 6 burning stages in the star: hydrogen, helium, okay, and then we have carbon burning, then we have silicon burning, then we have S process, all process, R process and P process, and then finally L process. So, in different burning stages this formula is going to play a very important role. So, please bear with me for a few lectures till I use this formula extensively. But before that, with the help of one numerical, let me discuss the importance of this formulae in deciding the dominant way of destruction of a particular nucleus. For example, okay, let me solve one interesting example for you. Okay. In stellar plasma, consider 25 aluminum, it can be destroyed by proton gamma. That means 25 aluminum reacting with proton, it emits 26 silicon. Okay. It can also undergo decay. Which kind of decay? Positron decay, okay, whose half life is equal to 7.2 seconds. Okay. Here you see aluminum 13, protons are more and neutrons are less, number of neutrons is 12. So, one proton tries to convert into neutron. So, as part of that it undergoes positron decay. Now, you assume only these two processes. Now, you have to say which process is dominating. Given data is T is equal to say 0.3 into 10 to the power of 9 kelvins, that means 0.3 gigakelvin, okay, and the given reaction rate is 1.8 into 10 to the power of minus 3 centimeter cube per mole per second, okay, and rho is 10 to the power of 4 grams per centimeter cube, and mass fraction of protons or hydrogen say 7.7. Okay. Now, let me first consider proton capture reaction. In proton capture reaction, what is the lifetime? By reacting with proton, type 1 nucleus here it is 25 aluminum and same formula you can use here, this one. Okay. So, rho, it is mass fraction of protons, mass of protons, okay, Avogadro number, sigma v. If you calculate this, okay, rho is 10 to the power of 4, okay, and mass fraction is 0.4, this is 1.078 AMU, and Na into the reaction rate is already given here. If you calculate this, it is about 0.08 seconds. Similarly, the second way of destruction, that is beta decay. What is the lifetime of 25 aluminum by undergoing beta plus process is nothing but half life of the beta plus decay divided by logarithm of 2. This is a well known relation to you, right. So, 7.2 seconds divided by 0.693, this gives me around 10.4 seconds. What does it mean? The lifetime of aluminum 25 via beta plus decay is 10.4 seconds, whereas the lifetime of aluminum 25 by reacting with protons, because protons are in abundant, right, it is 0.08 seconds. So, where is 10 seconds and 0.08 seconds? So, what is the conclusion? The dominant way of destruction is proton induced reaction. Remember, aluminum 25 is not a stable nucleus, it is radioactive. So, it is always free to undergo destruction simply by decaying. Simply by decaying, it will lose its existence, right. But before undergoing decay, because of the mass fraction and number density available, the stellar density, which further depends on the temperature, proton capture proved to be dominant way of destruction mechanism. So, this kind of concept is important to understand the evolution of aluminum 25. Here I have taken one simple example of aluminum 25. I hope it is clear to you how to determine which process is dominant by taking the help of mean lifetime of a nucleus via decay and via particle induced reactions. So, with this knowledge, we are in a position to write down expression for the evolution of aluminum 25 nucleus considering all possible processes, Okay. So, for that let me write down the time dependent evolution of aluminum 25. For that let me tell you same example, aluminum 25 can be produced by reaction between Mg and proton, which gives rise to 25 aluminum. Okay. Not only that, alpha also can undergo with a nucleus, that is magnesium, which again produces 25 Al. Okay. Not only that, there is a nucleus 25 silicon, which undergoes positron decay giving rise to neutrino, okay, that also can produce aluminum 25. Not only that, if enough energy is available, gamma can react with 26 silicon, okay, producing proton and 25 aluminum. So, these are all ways of production and can be destroyed by reverse processes, right. For example, 25 aluminum can undergo destruction by reacting with proton giving rise to 26 silicon, and 25 aluminum can also react with available alpha particle and producing proton and also 28 silicon, and this 25 aluminum being radioactive, it can undergo positron decay, okay, producing 25 Mg. This is not of our concern. The main concern is this 25 aluminum, how it is undergo destruction. And 25 aluminum, it can also undergo reaction photo disintegration process with gamma, giving rise to 24 Mg. So, you can see the equivalence between these processes and these processes in inverse and forward direction. So, the time evolution of 25 aluminum abundance is described by the expression number density of aluminum 25 divided by dt, okay, d by dt of number density of aluminum 25. This is called as time evolution of abundance of aluminum 25. Now, let me write down number density of protons and number density of magnesium 24 sigma V. This reaction is between 24 mg P gamma 25 Al, right. This is one way of producing the aluminum 25, and second way is this one, right, alpha plus 22 mg. First one we have written, and second one number density of alpha and number density of magnesium, and a reaction between both of them, that is 22 mg alpha P producing 25 aluminum. What is the third way of producing 25 aluminum? Silicon 25 can undergo positron decay. So, what is its decay constant? This is the one, okay, beta plus nu, which is giving rise to 25 aluminum. Plus, not only that, it can also undergo destruction by reacting with gamma. So, what is the disintegration constant? Okay, 26 silicon gamma P. So, this other than these 4 processes, if there are more processes, I am using the symbol dot dot. Now, we are talking about time dependent abundance evolution of aluminum 25. So, this is not complete expression. I have written the possible ways for producing aluminum 25, but the moment they are produced, they are also undergoing destruction via these 4 processes which I have written earlier. So, those things also should be included in the expression of abundance evolution of aluminum 25. So, how to write down? Like this, minus N P N 25 aluminum sigma V 25 aluminum by reacting with P gamma, it is giving 26 silicon, minus second process is aluminum 25 can undergo destruction by reacting with alpha particle, is not it? So, sigma V 25 aluminum alpha P minus, at the same time this aluminum 25 nucleus can undergo decay also, and the decay constant depends on this particular value beta plus nu giving rise to 25 mg, and here of course 28 silicon. Now, the last process which we are considering at this place is 25 aluminum lambda 25 aluminum reacting with gamma proton minus these things. So, I strongly suggest you to write down a general expression for time dependent abundance and evolution of a general nucleus considering 3 processes. Number 1, particle induced reactions, number 2, decay process, number 3, photo disintegration. And beyond this, if any reaction comes to your mind, please include that. And like this, for every nucleus one has to write down the time dependent abundance evolution, okay. And for all the nuclei whose information is available, if you write down, then that is called as reaction network, and depending on the situation one can solve this reaction network analytically or numerically, all right. So, to summarize today's lecture, I have discussed mean lifetime of a particular nucleus, how it can be related to mass fraction and stellar density of another type of nucleus with which it is interacting and undergoing destruction, because of which we are discussing the concept of lifetime. And then I have discussed one example where by having the data of stellar density, mass fraction, reaction rate, one can find out the dominant way of destruction of a particular nucleus. And finally, time dependent abundance evolution equation I have written by taking the example of aluminum 25. Okay. I hope these things are clear to you, and please do not forget to write down a general expression, which is a homework for you, a general expression for time dependent abundance evolution of a specific nucleus, okay, considering all general processes like particle induced, decay and photo disintegration. In the next lecture, I will start charged particle induced reactions and neutron induced reactions in detail. Thank you so much for your attention.